So after talking about implicit differentiation today, Nicole asked a really good question. Does d dx of y squared equal 0, or does it equal 2y times y prime? And the answer to that's a little bit ambiguous, but the important thing is it depends on the context of the problem, or if there is context to that problem. So before I try to explain that a little bit more, let's just go back over Leibniz notation and try to understand what it's talking about. So whenever I have d dx of something, that means to treat x as the independent variable, i.e. we take the derivative with respect to that variable. So whatever this is, we're going to treat whatever variables in our denominator as the independent variable. So if I say d dx of x cubed, the key thing here is first x is the independent variable, and then these two variables are the same. So whenever these two variables are the same, we can differentiate normally. And so we know that we just follow the power rule here, and we get d dx of x cubed is equal to 3x squared. Now that allows us some flexibility for other variables, so that if I write d dr of pi r squared, like that, then here's my independent variable. The key thing is those two are the same, and so I can differentiate normally. Remember that pi is a constant, so it'll stay attached, and so I would just follow the power rule. I get pi times 2r to the first, or we would typically write that as 2 pi r, like that. Now an example that's just like that is, say I tell you to find d dv of p times v squared. All right, and without any further context, here's my independent variable, and so what that says is, without any further context, that's going to be important later, but without any further context, I can treat that p as a constant, like that, and then I'm just differentiating v squared. So this is exactly like the example up above, where I would just say p times 2v to the first power, and I might rewrite that as 2 times pv. All right, so that's the key thing there. Now, so now back to Nicole's question. Say I have d dx of y squared, okay, with no context to this problem, then I'm going to treat that y squared as a constant, like that, and so in this case, I'm trying to differentiate a constant, so I would get 0. All right. Now, where things are a little bit different is if we're doing implicit differentiation. Whenever you're doing implicit differentiation, there's context here. The context is that we're assuming y is a function of x. Okay? And so that changes the game. There's new context to this. So then, if I'm doing d dx of y squared, all right, y is no longer a constant. It's a function of x. And so, if you need to do this, it's a little bit more cluttered. And so we could rewrite that y as y of x squared. Okay, so now the game changes. Here I have a composition. That I have that y of x is inside the squaring function. Like that. So I would follow the chain rule. All right, and so to do that derivative, I would differentiate the outside. So I'd bring down that 2, and I would have y of x raised to the first power, not a prime, to the first power. That's the derivative of the outside. But then remember what the chain rule says. That's a first power, by the way. What the chain rule says is I do the derivative of the inside. The other part that's a little strange to people is I'm just going to write y prime at x. So we're used to actually taking a derivative at this point, but the problem is that we don't know what the equation for y of x is, so we'll just write y prime at x. That's the best we can do. Now, as you can see, there's enough clutter here already, and this dependence on x kind of adds to the clutter, so we often take it out, and so we'll just say 2y to the first times y prime, or just 2y times y prime. Now, the key thing is, I illustrated this in class, so the key concept is if you're assuming y is a function of x, you just take this derivative normally, that's the 2y part, and then you just multiply times y prime, and that's the derivative of the inside part. So likewise, as long as you're assuming y is a function of x, d dx of something like 3y to the fourth, I could differentiate it normally, so I get 3 times 4y cubed, like that, and that's just a regular derivative, but since I differentiated a function of y, I multiplied times basically the derivative of the inside, which is y prime. And so we'd say that that's 12y cubed, y prime. Again, if you're doing implicit differentiation so that you're making this assumption y is a function of x. Alright, I hope that helps, and I'm also going to post a video with just some implicit differentiation examples. Thanks.